Your home keeps you warm without asking you to think about it. Insulated walls, stable foundations, and controlled indoor temperatures feel like modern inventions, but their origins stretch back to the Ice Age. During that time, surviving winter depended on one challenge above all others: building a shelter that could hold heat. Fire alone was never enough. Heat escaped into the freezing air, forcing people to burn more fuel just to survive. The breakthrough came not from building bigger fires, but from understanding the ground beneath their feet. Early humans discovered that the soil stayed far more stable than the air above. By digging shelters partially underground, they used the surrounding earth to block the wind, slow heat loss, and trap warmth. For the first time, humans engineered their environment instead of simply hiding from it. The underground shelter became the foundation for every innovation that followed. The story begins with one simple question: why did humans start building underground instead of above the ground? If staying warm was the key to survival, caves seemed like the perfect solution. They blocked the wind and offered immediate shelter. But Ice Age humans soon discovered they could never be a reliable long-term home. The first problem was availability. Suitable caves were rare across the vast Ice Age grasslands, and many hunting territories had none at all. Even when a cave was available, it brought new dangers. Damp walls and wet floors accelerated heat loss. Enclosed spaces trapped smoke from indoor fires, while cave bears, cave lions, and other predators often claimed the same shelters. Most importantly, caves forced people to live where nature allowed, not where hunting, water, or seasonal resources were best. Instead of searching for the perfect cave, humans made a revolutionary decision. They would build their own shelter. That decision marked the first step toward the underground house, giving people control over where they lived, how they built, and how efficiently they could conserve heat. The next challenge was finding a material that could replace the protection caves once provided. After abandoning caves, humans needed a new way to survive the Ice Age winter. The answer was not in wood or stone, but in the ground beneath their feet. Over generations, they discovered that while the air changed with every storm, the soil below remained far more stable. Just a few feet underground, temperatures fluctuated far less than the freezing air above. That discovery led to a simple but revolutionary idea. Instead of building entirely above ground, people dug their shelters into the earth. The surrounding soil became a natural layer of insulation, blocking the wind, slowing heat loss, and helping a fire stay warm with far less fuel. The earth was no longer just the ground they walked on. It became the first building material of the underground house. This marked the beginning of earth-sheltered construction, a design that worked with nature instead of against it. But one question remained. If digging underground made a shelter warmer, how deep should it be? Discovering that the earth could hold warmth was only the first step. The next challenge was finding the depth where that natural insulation worked best. Archaeologists have uncovered circular pits dug to remarkably consistent depths, showing they were carefully planned rather than randomly excavated. Early humans learned that shallow shelters remained exposed to the freezing air, while deeper ones benefited from the Earth's far more stable temperature. Without thermometers or scientific instruments, they found this optimal depth through generations of observation and experience. That knowledge became the foundation of underground construction. The pit was no longer just a hole in the ground. It became the foundation of a carefully engineered home, using the earth itself to reduce heat loss before the first wall or roof was built. Once the ideal depth was established, the next challenge was turning that excavation into a structure strong enough to survive an Ice Age winter. Reaching the right depth solved the problem of insulation, but not strength. An underground pit could only become a home if it could safely support a roof through months of snow and freezing weather. Ice Age builders constructed a structural frame above the excavated pit while the surrounding earth formed the lower walls. Where timber was plentiful, sturdy wooden poles supported the roof. Across the Mammoth steppe, where wood was scarce, they turned to another material. Mammoth bones became the framework. Large skulls formed stable foundations, while tusks and long leg bones created the main supports. Smaller bones reinforced the structure and distributed the weight before the shelter was covered with hides, vegetation, and earth. The frame and the surrounding soil worked as one system. The earth provided insulation, while the frame carried the load. A simple pit had become a durable underground house, built to withstand the harsh Ice Age climate. With the structure complete, builders could focus on the next challenge, creating layers that kept precious heat inside. A strong frame could support the shelter, but it could not keep people warm on its own. Preventing heat loss required more than a single building material. It required layers. The frame formed the shelter's skeleton. Animal hides blocked the wind. Dry grasses, moss, and other plant materials trapped still air and slowed heat loss. Finally, the entire structure was covered with earth, blending it into the landscape. During winter, snow added another layer of natural insulation. Each layer served a different purpose. The frame carried the load. The hides stopped the wind. The vegetation reduced heat transfer. The earth stabilized temperature, while snow provided additional protection against the freezing air. No single material kept the shelter warm. Its efficiency came from combining multiple layers into one integrated system. The underground house was no longer just a covered pit. It had become a carefully engineered thermal system. One part of that system deserves special attention because an unusual material made this design possible across the treeless Mammoth steppe. Across the open Mammoth steppe, wood was often too scarce to build large shelters. Instead of abandoning underground construction, Ice Age builders adapted by using mammoth bones as structural materials. Massive skulls anchored the structure, while tusks and long leg bones formed strong curved supports. Jawbones and smaller bones reinforced the framework, helping distribute the weight before the shelter was sealed with hides, insulation, and earth. This was more than using whatever materials were available. Each bone served a structural purpose, allowing the shelter to withstand heavy snow, strong winds, and months of freezing weather. Combined with the underground foundation and layered insulation, the bone framework created a remarkably efficient home. Modern reconstructions suggest these shelters could remain dramatically warmer than the air outside while requiring only modest fires. Their success came from the entire system working together. The underground pit reduced heat loss, the insulated layers trapped warmth, and the mammoth bone framework held everything in place. Even this highly efficient design faced one invisible threat that developed inside the shelter itself. By now, the underground house could retain heat, block the wind, and protect its occupants from the brutal Ice Age climate. But the better it trapped warmth, the greater a hidden problem became. The enemy was moisture. Every breath, cooking fire, melting snow, and drying hide released water vapor into the shelter. With nowhere to escape, the warm, humid air condensed on the colder walls and roof. As temperatures fell, that moisture froze, soaking the insulation and reducing its ability to retain heat. Moisture also damaged the shelter itself. Wet hides deteriorated faster, plant insulation lost its effectiveness, and ice forming between building materials gradually weakened the structure. The fire created another challenge. It provided the heat needed for survival, but also filled the shelter with smoke. Sealing the house preserved warmth but trapped moisture and stale air. Opening it too much cleared the air but allowed precious heat to escape. The underground house had become more than a shelter. It was a carefully balanced system where insulation, temperature, moisture, and airflow all had to work together. Solving that balance required another innovation, allowing the house to breathe without losing most of its heat. Solving the moisture problem did not mean sealing the underground house. Instead, Ice Age builders learned that a successful shelter had to breathe while conserving heat. They created a simple passive ventilation system using carefully placed openings. Cool! Fresh air entered through lower vents, while warmer air carrying smoke, moisture, and stale air naturally escaped through higher openings. This continuous airflow required no mechanical devices. It relied entirely on warm air rising, while the fire helped maintain circulation throughout the shelter. Because the openings were small and carefully positioned, most of the heat stayed inside. At the same time, excess moisture and smoke were steadily removed, protecting both the people and the structure. Insulation and ventilation were not competing systems. They worked together to keep the underground house warm, dry, and breathable throughout the winter. With clean air flowing through the shelter, one essential element still determined whether the entire system could function. That element was the fire at the center of the house. Even the best underground house could not survive an Ice Age winter without a reliable source of heat. At the center of that system was the fire. The hearth was typically placed near the center of the shelter, so its warmth could spread evenly. The surrounding earth and insulating layers absorbed part of that heat and released it gradually, helping the interior stay warm long after the flames had weakened. The fire did more than provide warmth. It melted snow into drinking water, cooked food, dried clothing and hides, and helped reduce moisture inside the shelter. But it also required careful control. A fire that burned too large wasted fuel and produced excess smoke. A fire that burned too small allowed the shelter to lose heat. Builders adjusted the flames according to the weather, available fuel, and the needs of the people inside. The underground house was designed to work with the fire, not depend on a massive one. Efficient insulation allowed even a modest fire to keep the shelter warm while using far less fuel. Once the heating system was optimized, one challenge remained. The fire could only keep burning if enough fuel had been gathered and protected before winter arrived. A warm underground house was only as reliable as the fuel that kept its fire burning. Once the fire went out, the shelter gradually lost its heat, no matter how well it was built. Fuel management became an essential part of survival. Before winter arrived, people gathered the best fuel their environment could provide. Where wood was scarce, they relied on dried animal dung, grasses, shrubs, and processed bones, choosing materials that burned efficiently. Keeping fuel dry was just as important as collecting it. Supplies were stored inside the shelter or under protective coverings, ensuring the fire could always be relit when needed. Fuel also had to last through the entire winter. Instead of maintaining large fires, people used small controlled flames that worked with the shelter's insulated design. Because the underground house retained heat so effectively, it required far less fuel than an exposed shelter. Better insulation reduced fuel consumption. Lower fuel consumption meant fewer dangerous trips outside during severe weather. With heat secured, the next challenge was making sure food would last just as long as the winter itself. An underground house could not be built after winter arrived. Frozen ground was difficult to dig, heavy snow slowed construction, and gathering materials became far more challenging. Survival depended on finishing the shelter before the cold set in. Preparation began months earlier. While the ground was still workable, people selected the site, excavated the shelter, built the frame, installed the insulation, and covered the roof before the first major snowfall. Every essential material had to be ready. Animal hides were cleaned and dried, grasses and moss collected, bones or timber assembled, and enough earth prepared to seal the structure. Fuel and preserved food were also stored before severe weather made travel difficult. Each step depended on the others. An unfinished roof exposed the shelter to snow. Missing insulation allowed heat to escape. Too little fuel weakened the entire heating system. Building an underground house was not an emergency response. It was a carefully planned seasonal project. By the time winter arrived, the shelter, its insulation, ventilation, heating system, and supplies were already in place. With the house ready for winter, attention turned to preserving enough food for the months ahead. Keeping the underground house warm was only part of surviving winter. It also had to preserve food for the months when hunting became difficult or impossible. The stable temperature beneath the ground made the shelter an ideal storage space. Unlike the rapidly changing conditions above the surface, the underground environment protected preserved food from repeated freezing, thawing, and excess moisture. Dried meat, rendered fat, marrow, and other stored foods were kept in carefully chosen areas, safe from snow, wind, and direct sunlight. Supplies were organized to stay clean, dry, and easy to access while reducing contamination from ash, smoke, and moisture. The underground house now served two essential purposes. It conserved heat while protecting the food needed to survive the entire winter. Efficient insulation reduced the need for fuel, while reliable food storage reduced the need to leave the shelter during severe weather. The next step was extending that protection beyond the shelter itself. The underground house protected people indoors, but surviving the Ice Age also required carrying that protection outside. Clothing became an extension of the shelter itself. Using finely crafted bone needles, Ice Age builders stitched animal hides into fitted garments instead of simply draping them over the body. Like the house, the clothing relied on layers. Fur faced inward to trap warm air, while tougher outer hides blocked wind, snow, and moisture. Different hides served different purposes, creating a system in which every layer had a specific role. The same engineering principle worked both inside and outside the shelter. The underground house conserved heat for the living space, while layered clothing conserved heat for the individual. Together, they formed one continuous system of protection, preserving warmth whether people were inside the shelter or crossing the frozen landscape. Even the best house and clothing, however, could only remain effective with constant maintenance. Building the underground house was not the end of the work. To stay warm, safe, and efficient through repeated winters, the shelter required constant maintenance. Builders regularly repaired damaged hides, replaced worn insulation, reinforced weakened structural elements, and fixed areas affected by moisture, snow, or daily use. Small problems were corrected before they became serious. Maintenance extended to every part of the system. The insulation had to stay dry, ventilation passages had to remain open, the hearth had to burn efficiently, and stored fuel and food had to stay protected. The underground house was never treated as a finished structure. It was a living system that required continuous care. Regular maintenance kept it performing through the harshest Ice Age winters. This commitment to maintenance allowed the shelter to remain reliable year after year, showing that a well-designed home depended not only on how it was built, but also on how it was cared for. The remains of these shelters would eventually reveal that engineering to archaeologists thousands of years later. Thousands of years after these underground houses disappeared, archaeologists uncovered their foundations, structural materials, and construction techniques. The evidence revealed far more than simple prehistoric shelters. It revealed carefully engineered systems. Although their builders left no written records, the remains show a clear understanding of structural support, insulation, airflow, and heat conservation. Every major component served a practical purpose and worked as part of an integrated design. Rather than uncovering crude dwellings, archaeologists found homes that were deliberately planned, carefully built, and continuously improved to withstand one of the harshest climates in human history. These discoveries transformed our understanding of Ice Age builders. Their underground houses were not accidental solutions, but the result of practical engineering refined through generations of observation and experience. The more archaeologists studied these shelters, the more familiar their design principles became. Thousands of years separate modern buildings from Ice Age underground houses, yet many of the same engineering principles remain. Modern earth-sheltered buildings still use the surrounding soil to stabilize indoor temperatures. Layered insulation reduces heat loss, controlled ventilation removes stale air while conserving energy, and efficient heating systems deliver more warmth with less fuel. The materials have changed, but the principles have not. Instead of fighting the environment, modern buildings often work with it, using natural insulation, passive energy efficiency, and environmental control to create warmer, safer, and more efficient homes. The underground house was more than a solution for surviving winter. Its engineering principles continue to shape the way buildings are designed today. Those ideas became the foundation of a tradition that began with humanity's first engineers. The greatest achievement of Ice Age people was not simply surviving the cold. It was creating an underground house that worked as a complete engineering system. Every part of the shelter had a purpose. The excavated ground provided natural insulation. The structural frame supported the roof. Layered walls conserved heat. Ventilation controlled moisture and smoke. The hearth supplied warmth, while fuel storage, food storage, clothing, and regular maintenance kept the entire system running through winter. None of these elements worked alone. Together, they formed one of humanity's earliest examples of integrated building design, where every component improved the performance of the whole shelter. Although the houses themselves disappeared long ago, the engineering principles behind them endured. They became the foundation for later advances in energy-efficient construction and environmental design. The first underground houses were more than places to live. They marked the beginning of human engineering, proving that understanding nature could be more powerful than fighting it.